Hello, welcome to another module in this massive open online course. So, we are looking at several example problems to understand the application of Z transform. So, let us continue this discussion. So, we are looking at various example problems for the Z transform. Okay. So, we already done 3 examples. Let us look at the 4th example. So, we want to use the power series approach, to find the inverse Z transform of 1 over 1 minus A Z inverse magnitude of Z is greater than magnitude of Z is greater than magnitude of A. So, now remember this is of the form the ROC is of the form, remember this is your ROC and the ROC is of the form magnitude of Z is greater than magnitude of A. We can even make this as a real number. Let us look at magnitude of Z greater than A, real positive number, magnitude of Z greater than A. So, ROC is of the form magnitude of Z is greater than A, therefore, this is a right handed signal. Okay. So, what we are looking at here, this is a right handed signal or a right sided. This is a right handed signal or this is a right sided sequence, correct. This is basically the kind of signal that we have here is basically a right handed signal. Okay. And now, to use the power series approach, what we are going to do is basically we will look at the numerator is 1 and we will divide that by the denominator. So, similar to the division, the long division, that is 1 minus A Z inverse. Okay. So, this is 1 minus A Z inverse. So, I multiply this by 1, that gives me 1 minus A Z inverse. Okay. So, you subtract this to now get the remainder is 1 minus, that is A Z inverse. Now, therefore, now you can multiply this by A Z inverse. Okay. So, if you multiply 1 minus A Z inverse, so now if you multiply 1 minus A Z inverse by A Z inverse, what you obtain is A Z inverse minus A square Z raised to minus 2, and now you can subtract this, and what this will give is A square Z raised to minus 2. Now, you can multiply by A square Z raised to minus 2, that will give you 1 minus A Z inverse multiplied by A square Z raised to minus 2 will give you A square Z raised to minus 2 minus A cube Z raised to minus 3, and now once you subtract it, you will have A cube Z raised to minus 3. Now, you can multiply by A cube Z raised to minus 3 and the procedure repeats. Okay. And now, you can see a pattern emerging. So, what you see when you divide this using long division, that is the power series approach, that gives us x z equals 1 over 1 minus A z inverse, that gives us 1 plus A z inverse plus A square z minus 2 plus a cube z minus 3 plus out. So, now what we have been able to do? We have been able to express this as a power series in z. Alright, we have been able to express this as xn z raised to minus n. Okay, so we have been able to express this as a power series in z, and now it follows that the sequence xn. So, this is nothing but, you can see this is a n z raised to minus n for n greater than or equal to 0, and therefore, the sequence is nothing but a n u n, that is for n greater than or equal to 0, it is a n. So, therefore, it follows from the power series, x of z that xn equals a raised to n u n. This is the sequence. So, you have constructed the power series, and from the power series the inverse z transform. Okay. So, the inverse z transform follows from the power series as xn equals a raised to n u n. Okay. So, this is basically the power series approach of constructing the inverse z transform. Let us now look at another example, example number 5. Let me just start it on a fresh page, I think that will make it much more convenient. So, we have a rational function of z, evaluate inverse z transform three z square minus 5 z by z square minus 3 z plus 2, and the ROC is given as magnitude z less than 1, and therefore, what this means is this is a left handed signal. From the ROC you can see that this is a left sided sequence or a left handed sequence. This is a left handed sequence, and we have to evaluate the inverse z transform of this. This is your x of z. Remember, this is a rational function of z, you can clearly see, and whenever we have a rational function of z, we can try to express this as a partial, you can use the partial fraction approach. So, this is a rational function, this is a rational function in z. Okay. And now, this can be done as follows. I can express x z, remember we have x z equals 3 z square minus 5 z divided by z minus 1 into z minus 2. I can express this as follows. Now, remember we said x z over z can be expressed as the partial fraction expansion is of the form c naught over z plus c 1 over z minus 1 plus c 2 over z minus 2. By the way, I forgot to mention that z square minus 3 z plus 2 can be expressed as z minus 1 into z minus 2. Now, remember there is one more step here. We have z square minus 3 z plus 2 equals z minus 1 into z minus 2. So, the poles of this are z equal to 1 and z equal to 2. So, poles are at z equal to 1 comma 2, this is a rational function, and obviously there are zeros, the zeros will be at 3 z square minus 5 z. So, 3 z square minus 5 z equal to 0 implies z into 3 z minus phi equal to 0 implies either z equal to 0 or z equal to phi by 3. So, these are the zeros, these are the zeros of the z transform. So, the poles are at 1 comma 2, zeros are at 0 comma phi by 3. Anyway, the zeros are not important for the partial fraction expansion. Remember, the partial fraction expansion depends only on the, the terms depend only on the poles. That is, to look at the structure of these different terms, we need knowledge of the poles. Okay. And so, basically what we are using here is we are using the partial fraction approach. So, this is the partial fraction expansion. We are using the partial fraction expansion, and now the various terms can be found as follows. Now, we know C naught is simply, that is x z evaluated at z equal to 0, that is basically your 3 z square minus 5 z divided by z minus 1 into z minus 2 evaluated at z equal to 0, and this is basically you can clearly see this is 0. So, C 0 is 0. Now, what about C 1? Now, C 1, remember C 1 is z minus 1 into x z over z evaluated at z equal to 1, that is basically 3 z minus 5 divided by z minus 2 evaluated at z equal to 1. So, this is 3 z minus 5 at z equal to 1, this is minus 2 divided by z minus 2 is minus 1. So, minus 2 divided by minus 1 is 2. So, C 1 equals 2, and similarly we have C 2 equals z minus 2 into x z over z evaluated at z equal to 2. So, this is your 3 z minus 5 divided by z minus 1 evaluated at z equal to 2. So, this is basically your 1 divided by 1 equals 1. Okay. So, basically what we have at the end of this is basically that C naught equals 0, C 1 equals 2 and C 2 equals 1. So, these are the coefficients in the partial fraction expansion. Okay. So, these are basically your coefficients in the partial fraction expansion of x z over z. Partial fraction expansion of x z over z, which implies, so now this implies that basically your x z over z can be written as x z over z can be written as twice over z minus 1 plus 1 over z minus 2, which basically implies that x z equals twice z divided by z minus 1 plus z divided by z minus 2, and remember the ROC remains, that is magnitude of z less than 1, and therefore, now if you look at the left handed sequence corresponding to this, that is, remember we use the property z by z minus a, I think z by z minus a for a left handed signal, that will be minus a raised to n u minus n minus 1, that is magnitude of z less than, the ROC is magnitude of z less than a. So, this would be 2 z. So, this would be minus 2, the pole is 1. So, this would be a to the power of n would be 1 to the power of n, which would be 1. So, this would be minus 2 u of minus n minus 1 minus z over z minus 2, that is 2 to the power of 2 raised to n u of minus n minus 1. So, this is basically your sequence x of n. X of n is minus 2 u minus n minus 1 minus 2 raised to n u of minus n minus 1. So, this is basically your solution. This is basically the inverse Z transform. This is basically the inverse Z transform. So, we are able to evaluate using the partial fraction expansion of x z over z, we are basically able to evaluate the inverse Z transform of the given rational function of Z. Okay. Let us look at another example again to find the inverse Z transform. So, once again we have to find the inverse Z transform. Find the inverse Z transform of x z equals z times minus z square plus 5 z minus 5 divided by z minus 2 times z minus 3 whole square. The ROC is 2 less than magnitude of z less than 3. So, remember this is a infinite signal, because remember the ROC of the form is it lies between two poles 2 and 3, alright. So, you can see the poles are 2 and 3, ROC lies between 2 and 3, correct. So, this is an infinite signal from minus infinity to infinity. So, from the ROC itself we can see this is an infinite signal. That is spans minus infinity to infinity. Okay. And now you can see there is a multiple. Now, previously you had simple poles, right. Now you have repeated poles. Now, you have multiple poles of multiplicity greater than 1. For instance, the poles here you can clearly see the poles are z equal to 2 and 3, but at z equal to 3 you have pole of multiplicity 2. Multiplicity equals 2, okay. And therefore, if you look at the partial fraction expansion of x z over z, that will be of the form x z over z equals c naught by z plus C1 by z minus 2, plus we will have to corresponding to pole at z equal to 3 of multiplicity 2, we will have two terms lambda 1 by z minus 3 plus lambda 2 by z minus 3 by z minus 3 whole square. Okay. Now, coming to C naught. C naught is x z evaluated at z equal to 0, and this is easy. C naught is 0, x z evaluated at z equal to 0, this is 0. So, we have C naught is basically equal to 0. So, the coefficient corresponding to z, that is C naught by z, the coefficient C naught in the partial fraction expansion of x z by z, C naught is 0. Let us look at C1. Now, C1 is also relatively simple to find. C1 equals z minus 2, this corresponds to the simple pole, that is pole of multiplicity 1, z minus 2 x z over z at z equals 2. This is basically your minus z square plus phi z minus 5 divided by z minus 3 whole square evaluated at z equal to 2. So, this is equal to, what is this equal to? This is equal to, basically you will have minus 4. So, evaluate the numerator at 2, minus 4 plus 5 2s are 10 minus 5 divided by 2 minus 3 whole square, 1 square, that is 1. So, this will basically be 10 minus 4, 10 minus 9. So, this is 1 divided by 1, which is equal to 1. So, C1 equals 1. Okay. So, what we are able to establish is that C1 is equal to 1. Okay. Now, what about lambda 2? Now, lambda 2, that is the coefficient corresponding to z minus 3 whole square. So, that can be evaluated as z minus 3 whole square x z over z evaluated at z equal to 3. So, that will simply be minus z square plus 5z minus 5 over z minus 2 evaluated at z equal to 3. So, this will be equal to minus 9 plus 15 minus 5 divided by 1. So, this will be basically 1. So, lambda 2 equals 1. Now, what about lambda 1? Remember, we can find this using this formula. If you go all the way back, let me just refresh your mind, refresh your memory regarding the formula that we are going to use. That is, we are going to use the formula that lambda r minus k. Remember, look at this formula, lambda r minus k is 1 over k factorial, the kth derivative dk or dzk, z minus pi raised to the power of k x z over z. I am sorry, this should be, I think, z minus pi raised to the power of r. I think that should be z minus pi raised to the power of r. Z minus pi raised to the power of r x z over z at z equal to pi. Okay. So, this is basically what that turns out to is, remember, r is equal to, in this case r is equal to 2, we have r is equal to 2. So, I have lambda 1 equals lambda r 2 minus 1. Okay. So, k equal to 1. So, r minus k equals 1 over k factorial. So, 1 over 1 factorial times d over the kth derivative, k equals 1 in this case. So, d by simply d by dz times z minus 3 whole square into x z evaluated at z equals 3. Now, let us evaluate what this quantity z minus 3 whole square x z is. Z minus 3 whole square x z, I am sorry, z minus 3 whole square x z over z, z minus 3 whole square x z over z. Now, this quantity, if you look at this, the z minus 3 whole square x z over z is minus z square plus 5z minus 5 divided by z minus 2, which is basically, you can write this as minus z minus 2 whole square plus z minus 1, correct, divided by z minus 2, which is equal to minus z minus 2 plus, now z minus 1 can be written as z minus 2 plus 1, z minus 2. So, this will be minus z minus 2 plus 1 minus of z minus 2 plus 1 plus 1 by z minus 2, this is equal to minus z plus 3 plus 1 by z minus 2. This is your z minus 3 whole square z minus 3 whole square x z over z. Now, the derivative of this d over dz z minus 3 whole square x z over z, this will be the derivative of this will be well, the derivative of minus z is minus 1, derivative of 3 is 0, minus 1 over z minus 2 whole square, and this evaluated at z equal to, remember we have to evaluate this derivative d over dz z minus 3 whole square x z over z has to be evaluated at z equal to 3. So, that will be minus 1 over z minus 2 square minus 1 minus 1 minus 1, that is equal to minus 2. So, what we have is lambda 1 equals minus 2. So, we have basically lambda 1 equals minus 2, and therefore, we have x z over z equals 1 over z minus 2, that is your C 1, which is 1, plus lambda 1 lambda 2, remember lambda 2 is 1. So, 1 over z minus, so lambda plus lambda 1 over z minus 3, lambda 1 is minus 2. So, this will be minus 2 over z minus 3 plus lambda 2 over z minus 3 whole square, lambda 2 is 1. So, this is 1 over z minus 3 whole square, okay. And this is the partial fraction expansion of x z over z, okay. So, x z, therefore, this implies that x z equals z over z minus 2 plus twice z over z minus 3 plus z over minus twice z over z minus 3 plus z over z minus 3. Okay. So, this is basically the partial fraction expansion of now x z. Okay. And remember, the ROC still remains, the ROC is given as 2 less than magnitude of z less than 3, that is the ROC, alright. So, basically we are now able to derive the partial fraction expansion of x z over z. What we have to now do is basically compute the inverse z transform of each of the individual terms, alright, and from that we can reconstruct the individual the inverse, and putting them together we can reconstruct the inverse z transform of the given rational function of z, that is x of z, alright. So, we will stop this module here and we will continue with this example and look at also other examples in the subsequent module. Thank you very much.